Welcome to Math Science History. Today we are exploring the story and the myths surrounding Carl Friedrich Gauss, the Prince of Mathematics. This isn't because he chased fame, but because his insights were so deep they silently built the scaffolding of modern science. Hi, I'm Gabrielle Burchak. I'm a science communicator with a background in math, science, and journalism. And by the time you're done with today's podcast, you're going to see that Carl Gauss's influence is everywhere, especially in places we don't even think about. Today, we're taking a closer look at the life of Carl Friedrich Gauss, a man whose mind operated at a level that still amazes mathematicians, physicists, and engineers today. Gauss reshaped number theory, astronomy, magnetism, geodesy, statistics, and even the geometry that underlies Einstein's theory of relativity. Gauss was born in 1777 in Brunswick, Germany, to a working-class family with very little money. His father worked hard as a laborer, and his mother was illiterate. One of the most famous stories about Gauss comes from his son, Joseph, who said that when Gauss was a very young boy, maybe 7, maybe 10, depending on the retelling, his teacher assigned the class a tedious arithmetic task, adding the numbers from 1 to 100. According to this family recollection, Gauss looked down briefly, thought for a moment, and wrote the correct answer, 5,050. Now, was it exactly 1 through 100? Historians aren't sure. Did Gauss use the elegant pairing trick, 1 plus 100, 2 plus 99, each equaling 101? That part appears in later retellings, especially in Eric Temple Bell's more theatrical biography titled Men of Mathematics. What we do know is that Gauss displayed extraordinary speed, accuracy, and intuition in mathematics. So much that Gauss's teacher, J.G. Butner, and his assistant, Martin Bartels, recognized this unusual talent and advocated for his education. Their advocacy reached Charles William Ferdinand, the Duke of Brunswick, who agreed to fund Gauss's schooling. The Duke's sponsorship was significant because at this time, Germany offered virtually no path for a poor child to enter advanced study without a patron. Without that support, Gauss's life trajectory would have been dramatically limited, an inference grounded in socio-economic context, no doubt. By his early 20s, Gauss was doing work that would define entire fields. Then, at age 19, Gauss proved that a 17-sided polygon, the heptadecagon, could be constructed with a compass and a straight edge. No one had discovered a new constructible polygon in over 2 millennia. This breakthrough is fully documented in his personal notes. And he kept all of his notes, and eventually he incorporated all of this information into his work titled Disquisitione Arithmeticae, that is Latin for arithmetical investigations. He created this body of work when he was only 21 years old and published it at the age of 24 in the year 1801. It is one of the foundational texts of modern number theory. It formalized modular arithmetic, residue classes, quadratic reciprocity, the backbone of contemporary cryptography, and computational mathematics. This particular body of work was not only a stepping stone, but also brought a new level of challenge and thoroughness to the applications of number theory. It highlighted the topic and made it rigorous in education. In arithmetical investigations, he incorporated the works and the theories of Fermat, Euler, Lagrange, and Legendre, and presented number theory as systematic. But here is where Gauss's personality begins to emerge. He didn't celebrate. He didn't show off. He didn't boast about his groundbreaking work. In other words, if he were alive today, he probably wouldn't have an Instagram. In 1801, astronomers discovered a small celestial object, Ceres. Then they promptly lost it. Observational records were sparse, inaccurate, and scattered. To recover it months later, they needed to know its orbit, but determining a planet's path required knowing not just where it appears in the sky, but also how far away it is, how fast it's moving, and how its motion curves around the sun. Gauss realized that even with just 3 sightings, he could reconstruct the planet's path by combining a deep understanding of Kepler's laws with clever geometry. He treated each sighting as a line of sight from Earth and then worked backwards to estimate Ceres' actual position in space. Using those reconstructed positions, he pieced together the orbit's shape and tilt, the orientation of the ellipse, and where Ceres should reappear after nearly a year of darkness. The genius of Gauss's method wasn't exotic mathematics. It was his uncanny ability to visualize how all the pieces fit together and apply just enough algebra and trigonometry to predict precisely where astronomers needed to point their telescopes. And on the very first clear night after they tried Gauss's prediction, Ceres was found exactly where he said it would be. Gauss, only 24 years old, applied a new mathematical approach now known as the method of least squares to reconstruct Ceres' orbit with astonishing accuracy. This method of least squares became the backbone of mathematics, using statistical regression, error analysis, orbit determination, machine learning, geodesy, and signal processing. His achievements made him a legend. After his Ceres success in 1801, he continued his work in this area. By 1809, he was ready to publish his work titled Theory of the Motion of the Heavenly Bodies Moving About the Sun in Conic Sections, famously known as Theoria Motus. Theoria Motus was exceptional because he didn't just write a handbook on how planets move. He was laying down the mathematical tools that would shape how we calculate in astronomy, physics, and data science. Yep, data science, as we know it today. His book contained several significant contributions that are still used today, and we couldn't do our current calculations without his work. So in his book, Theoria Motus, he created the first fully systematic theory of orbit determination. Before Gauss, the methods for calculating orbits were inconsistent and unreliable. Gauss developed the very first complete, rigorous mathematical framework for determining the orbit of any celestial body from observational data. So don't get me wrong, other astronomers were able to calculate it, including Hypatia almost 2 millennia earlier, but it was the first complete framework. His methods showed how we can convert Earth-based measurements into heliocentric positions. Additionally, his methods showed how he could transform those positions into orbital elements and how to account for observational error. And finally, his methods showed how we can refine an orbit over time, thereby enabling future determinations of the orbit of a celestial body. But wait, there's more. In this body of work, Gauss also introduced the method of least squares. This method finds the best fit curve, or the orbit, by minimizing the sum of the squared errors. His methods are now used in machine learning, data modeling, statistics, economics, engineering, and physics. It's mind-blowing. Also, in Theoria Motus, he introduced a comprehensive theory of observational error that showed how measurement errors behave statistically, how to give importance to different observations, and how to combine imprecise data optimally. These are foundational to modern error analysis. In this work, Theoria Motus, he also addressed Kepler's equation. This particular equation relates time to a planet's position in its elliptical orbit. Gauss mastered this equation. He had developed efficient, iterative techniques that solved it quickly and accurately. Now, consider this. This was the early 19th century, in the year 1809, long before computers existed. And Gauss had basically channeled the mind of a computer to solve Kepler's equation. And as you know, I've been talking a lot about relativity lately and frame dragging in astronomical bodies, as you heard in my interview with Dr. Ronald Mallet. If you didn't get a chance to listen to that, please go back and give that one a listen. It is a fantastic interview with Dr. Ronald Mallet about time travel. But back to 1809. Gauss had developed and improved formulas for updating orbital elements using new observations. He gave early treatments of perturbations. Perturbations occur when planets tug on each other and distort orbits over time. These methods were more accurate than previous approaches. And as we realize today, Gauss's methods were essential for long-term predictions. Finally, through Theoria Motus, Gauss had turned orbit prediction into solvable mathematical pipelines. Astronomers finally had a structured, reliable, mathematically grounded method that held steadfast for over a century. Theoria Motus was so highly regarded that he received the medal from the Prince Primate Dahlberg and from the Royal Society of London. In fact, Gauss had become a member of all learned societies. All of them. Additionally, in 1810, he was to receive an endowment from the Institute of France, but at this time, France was engaged in the Napoleonic Wars against various German states. As a result, Gauss did not want to receive any of this money. So, the money was used by Sophie Germain, who purchased a pendulum clock that she then sent to Gauss, who genuinely treasured the clock. And as brilliant as he was equally demanding of the students he mentored, including Bernard Riemann and Richard Dedekind. Riemann often described him as rigorous, sharp, and quietly encouraging. I like that. But Gauss was not a public intellectual. He was introverted, private, and a perfectionist. He often refused to publish work he considered incomplete, leaving students and colleagues to marvel at ideas that he kept entirely to himself. Around the same time that he published Theoria Motus, he was struggling emotionally. On September 10, 1809, Gauss and his wife had a child, whom they named Ludwig. They referred to him as Louis. Sadly, though, as a result of complications from the birth of Louis, his wife, Johanna, passed away a month later on October 11. He loved her deeply and was severely grief-stricken. Then, 6 months later, Louis died in infancy. His life included deep personal sorrow. The death of his first wife and his child affected him profoundly. And his friends described him as dignified and restrained, even in grief. Many years later, in 1927, his grandson, Carl August Gauss, was going through his grandfather's papers and found a letter he had written to his wife shortly after she passed away. On these papers are actual traces of Gauss's tears. As much as he was a profound mathematician, his writings are on par. In this letter to his wife, he writes, quote, "Only this one thing, that your infinite kind-heartedness may always hover and float, living before me, helping me, poor son of earth that I am, to struggle after you as best I can." One of Gauss's most profound contributions comes from his work on curved surfaces. In 1828, Gauss published a paper titled General Investigations on Curved Surfaces. Tucked inside was a result he modestly called the Theorema Egregium. This is Latin for the remarkable theorem, and remarkable is not an exaggeration. What Gauss showed was that the curvature of a surface, how it bends or warps, is something you can measure entirely from within the surface without ever needing to step outside it and look at its shape from above. In other words, you don't have to hover in three-dimensional space to know whether a surface is flat, like a tabletop, curved like a sphere, or saddle-shaped like a Pringle. You can figure it out using only measurements taken on the surface itself. Distances, angles, and the way triangles behave give you all the information that you need. Theorema Egregium was revolutionary because it shattered the long-held belief that curvature required reference to an embedding in a higher dimensional space. Gauss's insight became the foundation of modern geometry. It ultimately influenced Einstein's general theory of relativity, where the surface is space-time itself. And it all traces back to that quietly published 1828 paper where Gauss revealed that surfaces carry their geometry within them, no outside perspective required. His Theorema Egregium established that curvature can be determined entirely from measurements within a surface without any need for an external reference frame. This brilliant insight laid conceptual groundwork that later allowed Riemann to extend geometry into the framework Einstein needed for relativity. Einstein, 100 years later. Einstein. This is just mind-blowing. No doubt, Einstein stood on Gauss's geometric shoulders. Today, Gauss's influence permeates nearly every corner of modern science, often so quietly that we forget the mathematics behind the tools we use. His work isn't historical footnotes. They are living tools embedded in technology millions of people use every day. When your phone gives you turn-by-turn directions, it relies on Gauss's coordinate systems. This framework allows satellites and receivers to describe positions with precision. When researchers train modern machine learning models, they depend on the Gaussian distribution and the method of least squares. These are statistical ideas that Gauss formalized more than 2 centuries ago. Astronomers still compute planetary motion using variations of Gaussian orbit determination, a technique born from Gauss's success in finding Ceres. Physicists use Gaussian surfaces to solve problems in electromagnetism, which is a cornerstone technique for understanding electric fields. And nearly every field that touches data, from psychology and public health to economics and astrophysics, continues to rely on the elegant curve that bears his name, the Gaussian bell curve. This mathematical shape quietly describes everything from test scores to quantum particles. Gauss didn't set out to shape the future. He pursued truth with remarkable clarity. Yet his ideas became the hidden architecture of the modern world. His mathematics lives in our technology, in our science, and in the way we understand uncertainty, motion, and even reality itself. Though Gauss's imprint has been invisibly woven into our daily lives, his genius has, no doubt, indelibly changed them. Gauss's humility reminds us that a life well lived is not measured by attention or acclaim, but by how we choose to show up each day. And with that being said, carpe diem, my friends. Thank you for listening. If you are interested in reading the transcripts on Gauss, or even looking at the resources that I referred to for this podcast, come visit me at mathsciencehistory.com and click on the link titled Transcriptorium. While you are there, also click on that coffee button and make a donation. It doesn't have to be large, it can be small, but every donation helps to keep this podcast up and running. If you want to listen to the podcast without any ads on your favorite podcast platform, come visit me at mathsciencehistory.supercast.com. There, you can sign up for ad-free podcasts with Math Science History. And before I conclude, I just want to remind you all that next week is December, and that means it's Puzzle Month. And I've got a special one. It's a 2-parter, so you'll have to listen to it on Tuesday next week, and then the following Tuesday to solve the entire puzzle. And there will be 3 tiers of winners. I will have first place, second place, and those who gave it a good go, answered it correctly, but maybe didn't get it in on time or got so close. So there's going to be merch for them too. So be sure to tune in next Tuesday for the first part of the December holiday puzzle. And until next time, carpe diem.